So hey, I'm Andre, and this is my presentation on MST algorithms, specifically Kruskal's algorithm versus Prim's algorithm. Before we begin, I wanted to talk just a little, on undirected weighted graphs. They're graphs like these, which have nodes and edges that go in both directions between each node, and each of these edges have a score or a weight. You can call it either or. You can have any amount of nodes and edges. And now the points of these algorithms is that they try to find the minimum spanning tree. So I'll have to explain what a minimum spanning tree is. They are trees that include all nodes without a cycle, so they'll never form a closed loop. And they do this while having the lowest cost possible. The minimum spanning tree, therefore, will have take the amount of nodes, it'll have -1 that edges. So the problem statement for these algorithms is, given a connected, undirected, and weighted graph, how do we find a minimum spanning tree of that graph? So how do we go from a graph like this to getting the tree like this? Also, I think I should note, all of the images you'll be seeing on these slides were made by my program. That's why there's no referral to the images down below. So what's the purpose of these algorithms? MSTs from undirected graphs are useful for many things. They build infrastructure. They can be used for map building and SLAM for robotics. They can make protein interaction networks, and they can do a whole lot of other stuff. And it's good to have these algorithms because large graphs are really hard to do by hand if you think about it. If you have like 100 nodes and 200 edges, it would be really difficult to draw that out by hand. And even if you could do that, it would take a very long time. So you would want to speed up the process in case you wanted to compare multiple different MSTs or get MSTs quickly. So let's get into the algorithm now. The overview of Kruskal's algorithm is that it works like this. You sort all of the edges by ascending weight from each edge. So if you have a graph with 3 edges, being like weight 3, weight 2, and weight 1, you'd have 1, 2, 3. Then you walk through the sorted edges and look at the two nodes to which the edge connects. If they're already unified, you don't include the edge. Otherwise, you do include it, and you'll group that edge with those two nodes. Then you keep repeating this process until all the vertices are put in the same group. So, examples for that. I'll have my code here, which I'll give to you in the email. But we're going to create a graph. I'm going to make a 6-node graph with, say, 8 edges. As this one right here, you can see the weights for each of the edges were randomly generated from 1 to 10. And here you have our 6 nodes from 0 to 5. And we have random edge connections like this. All right. So to start running, we're going to pick a random node, which is going to be 0. We're going to pick the lowest weight edge first, which is going to be this one because it's a 2. And we're going to do this, and then we're going to group the 3 and the 5, which is between these two edges, because the 3 and the 5 aren't grouped yet. So there we go. We have a 3 and a 5. This is one group, and now we're going to move on to the next smallest edge, which should be either this 3 or this 3. It doesn't really matter which one. Okay, it went to the one on the top, so now it's going to group the 0. Now that it grouped to the 0, we're going to go to the next smallest, which will be this 3 over here. We group this one to the 4. Perfect. And now we're going to go to the next smallest, which should be the 6, which goes to the 2. So we're going to group this 2. And now the next smallest edge is going to be the 7, which groups the 1. And perfect. We have our MST with a score of 21, because if you add up 3 plus 7 plus 2 plus 3 plus 6, you'll get 9, 11, 18, 21. So that was good, but that was for a simple graph. I'm going to make it a bit more complicated now. So how about 7 nodes? But let's cluster up more edges. Let's do 13 edges. Let's go 13 edges. So here's our graph. I'll let you look at it for a little bit. This one's a lot more clustered up, so it'll be harder to find the tree. So the starting point was this 2. This 2 is is the lowest one, this or this one. So you can start at either one, it doesn't matter. We made this group, and now we're going to move on here. We moved on to this. Then we're going to the 4. Now we should move to this 3, or this 3, or this 3. None of them could be either one. and it just keeps moving like this. So now it's going to this 3. And I want to get to a point where I can demonstrate a cycle. So if this 5, when this 5 is selected, I'll show you what I mean by a cycle. You get one near one over here. And now we're going to move to this 4, actually. And there we go. So this 4 is black. Why is this black? Because this creates a cycle. We're connecting 2 nodes that are already connected by the tree. And by drawing this black line, you could possibly close a loop, which we cannot do to find the minimum spanning tree. So the algorithm would detect that this is a cycle because both of these are already grouped. Both node 2 and node 1 is grouped. So it'll get rid of that. And it'll just keep moving on to the next one. So it moved on to this 5. That 5 had a new node, so it wasn't a cycle. Now it's going to move on to this 5. Oh, no, I actually found it already. I forgot. And then score 18. Perfect. I'll give you one more example on Kruskal's, but I'll make it another simple one. Let's do 6, 7. 6, 7. Yeah, I'll run through this one a bit more quickly, but as you can see, it just follows the steps on the algorithms. This one's a bit more interesting because now we have the 1, and here we're forming a second group, which we actually didn't get to see on the other ones, so I'm glad I did this. This second group is a 2, 3 connected here. So now, eventually, these 2 are going to merge together, but for now, we're just going to go to the next edge, which is this one here. Perfect. And then that 1 is going to be part of the green group. And now it's going to pick either of the 10 edges. Oops. Either of the 10 edges. So it shows this one, which is going to connect the groups. And now they're all going to get added to the green group because it's the biggest group, or the orange group, because the color changed. But still, the groups combine. And now we're going to have to iterate. This one would be a cycle, so we just need one more here. Let's see how the algorithm does. This is a cycle. It'll delete that. This is also a cycle. It'll delete that. Then perfect, we have this one here, which is not a cycle, and it's been found. So now, next step, found, and this one added to 32. This one is pretty interesting. We had a lot of 10s. That's why it's more expensive, but 32. So moving on from that. The pseudocode, which is I wrote this in Python, but the pseudocode for the Python I wrote is simply that you make an empty set of edges, then you sort all of those edges by increasing weight, then you make each vertex into its own set. So each vertex is just like a single set of itself. Then for each edge in the sorted list of edges that you made, you're going to find the set that contains U and find the set that contains V. U and V are the vertices that make that edge. And then if they're in different groups, you're going to add those to the empty set of edges, which might not be empty anymore. So you're going to add that to the set of edges, which makes them in the spanning tree. And then you're going to merge U and V. You're going to keep this loop going until the size of the minimum spanning tree is exactly 1 less the size of vertices, because once you get that, you know that there's no more edges needed for you to connect all of the points. So if you're reading the Python code, I did use this. However, because of the visualizations, it's got a lot more to it than that in the code I used. The code I used is like more complicated than this, but it's just because of the visualizations. The actual MST algorithm that I use, the Kruscal, is about this. So I'm going to talk a little bit about the running time. Fundamentally, any comparison-based sorting algorithm, doesn't matter if you use merge sort or like binary sort, anything like that, has a lower bound of n log n. So therefore, the sorting these edges takes e log e. And then because Kruskal's uses path compression and union by rank, so find u and find v would not be a constant time. But because Kruskal uses path compression and union, like these like speed up tricks, it basically approximates to constant time. For each edge, it makes a worst case scenario 2 find operations and 1 union, meaning it's 3 to the e, 3e, which would be a linear operation, which means the overall runtime would be big theta of e log e from the sorting, plus the big theta of e from the each edge operations, plus the constant you could add for the find u and find v, which would just be big theta e log e. So the advantages of Kruskal's is that it's pretty simple to understand. It's really good for edge-based data if you have it in lists, and it works really well on sparse graphs because it's actually pretty quick on sparse graphs. The disadvantage is that you do have to sort all the edges, which is really expensive in dense graphs. Like if you think you have like, I don't know, 15 nodes and then you have like 35 edges, it's going to be quite a lot longer to sort. And it's also bad for data represented by an adjacency matrix because all of the edges would need to be extracted from the adjacency matrix before they have to be sorted, which would just add it, make it a lot slower. So now we're going to move on to the second algorithm I did, which would be Prim's overview. Prim's algorithm, and I'm going to give it the overview. So what you do in Prim's algorithm is that you maintain a priority queue that sorts edges based on the minimum edge cost. And then you're going to use that priority queue to determine the next node visit. So you're going to start the algorithm on any node and iterate through all of the edges, adding them to the priority queue. Excuse me. And then while the priority queue isn't empty, and an MST hasn't been formed, you're going to dequeue the cheapest edge from the PQ. If it's used, you're going to skip it and then you go again. And once you finally get an unused cheap edge for this, you're going to mark the node as visited and add the edge of the MST. Then you're going to go to this new node and you're going to iterate over all of that node's edges and add all of them to PQ. So let me show an example of that, a few examples. Let's go to Prim. Let's keep the 9 nodes. Let's make it 14 edges. So once you go here, here's our starting undirected weighted graph, connected undirected weighted graph. Now, so we start at node 0 for this case, and you can see the priority queue on the right. So what is this saying? This is weight 4, 0, 2. So this represents this edge right here, which is the weight of 4, and it's connecting 0 to 2. Then 6, 0, 3 would represent the weight of 6, connecting 0 to 3, and likewise, weight of 9, 0 to 5. So in the next step, we pulled out the lowest weight from the queue, which was the 402, if you remember, and then we're moving on to 2. So we pull that one out, and we group this, and now we iterate. We keep the priority queue from before. If you remember, we still have the 603 and the 905, but now we also add the 125, because it's weight 1 connecting the 2 to 5, and the 727, which is this one right here. Basically, we iterated over this, and we added the unused edges from before. Then we go to the cheapest edge in the queue, which was this one weight. And there we go. We grouped it like this. And now again, you're going to add this 8 and this 6. This 9 was already added over here, so it doesn't get double added, obviously. Now, we're going to find the cheapest one, which is the 603, which is this one right here. And yep, we're going to go for that one. And then we're going to go there. And then we have this we got here, and then we're iterating, so we're going to add the 434 and the 228, the 238, and it's going to go to this one. So selected the cheapest one there, and now it's going to go here. It added this one and this one and this one. And again, just iterates through all of the new ones and adds them to the priority queue. And you're going to keep moving along until every single vertex is accounted for. So we can see there. Now it's going to add these, and it's going to go to the cheapest, which should be this 3. Then it's going to add all of these, and it should go to the cheapest, which is the 1 now. Nice and easy. And now it's got all of these, and it's going to go to the cheapest, which interestingly is this 4 over here, which is going to be a cycle. Let's see how it adapts to that. See, it shows this black, but since it shows the 4 line here, but since it was a cycle, this would form a closed loop. It's going to get rejected because you can see that both 3 and 4 are already grouped. So we skip that one, and we go to the next best one now. So let's choose another one. This one over here, which was a 7 weight, but this is also a cycle. So we're going to ignore that. Then we're going to go to this one. It's going to take a while, but there we go. The 8 is also a cycle. We're ignoring that. Then the 9 over there is also a cycle. And finally, actually, there's still a chance the next one's a cycle as well. This 9, perfect. You pick this one. And perfect, we got our MST after you pick that 9 with a score of 29. If you add up all of the weights inside the red MST tree here, you would get a score of 29. Right, I'll do one more example, maybe 2, but probably just one more. I'll make it really short because I don't want to go through 15 cycles again. Let's go for 5, 7. This is our graph. You can see 0 here. It starts at 0, but it can start anywhere. We pick the smallest one. Then we add these to the priority queue and proceed to pick the smallest one again. Just this one here. Then we add the new one to the priority queue and pick the smallest one, which, there we go. Now that these are grouped, we're going to add this to the priority queue and pick the smallest one. And perfect, we got our MST with the score 14 for this. So the pseudocode I use for prim is you again take the MST and you set it to an empty set of edges. Then you also make an empty set of vertices. And then you put start into visited. And then you also initiate a empty of priority queue. So then for each neighbor via start, remember neighbor is any node that's connected like via one edge. You're going to insert the edge into PQ. So for all of its neighbors, you're going to take all of those edges and insert them all into PQ. And then while PQ is not empty and the size of visited, remember visited, is smaller than the total amount of nodes, because if it was equal to the total amount of nodes, when it becomes equal to the total amount of nodes, we have the minimum spanning tree. So when we get that, we're going to do extract the minimum weight from PQ, and then we're going to see if V is already visited. If it is, you're going to skip. If it's not, you're going to add that edge to the minimum spanning tree, and you're going to add V to visited. And then, for each neighbor x of V, which means for each of the neighbors of that new node, I apologize, for that new node, you're going to insert that edge into the PQ, and you're just going to keep repeating the system all the way until this loop stops. So just to go over one more time, this is the pseudocode, which is the basis which I wrote the Python code for. I wrote Python code that basically follows the pseudocode. The only difference is that I added a lot of visualization stuff in the Python code. That's why it's much longer than just a pseudocode would be. Now, moving on to the prim algorithm's running time. Fundamentally, a binary heap priority queue, or honestly any priority queue, I just use the binary heap one for that matter, would require a big theta of log e time per push pop operation. And then prim's algorithm performs a linear amount of such operations, giving big theta e log e for this part of the code. And then each adjacency list is scanned once, which gives big theta e. Thus the overall runtime would be big theta e log e plus the big theta e, but because big theta e is not the dominant term, we just say big theta e log e. Now, because log e equals big theta of log v squared, because any simple graph can have at most edges, like can't have more edges than vertices squared, because if they did, it wouldn't be a simple graph anymore, as there would be edges looping back on themselves. So like one node would have an edge which connects to itself. And in those cases, these MST algorithms don't work. So we can assume that log e here would equal log of v, which would mean that the total runtime for this algorithm would be big theta of e log v. The advantages, disadvantages this of prims. So this is very efficient if the graph has many edges, because if you compare it to like Kruskal's, it's much faster at handling each edge individually, and it's more limited by e log v, v being the vertices. It works well with adjacency lists and matrices because you don't really have to reform the data like you would do in Kruskal's, and it grows one single component. If you remember that third example in the Kruskal's algorithm, it can grow multiple different groups, which makes it a bit hard for real-time systems and a little bit harder to follow. This one will always just have from one center clustering out, which is a lot better. The disadvantage is that it requires a good priority queue to reach optimal performance. If you just use a normal list as a priority queue, you're going to run into like a much slower algorithm than e log v. It's harder to parallelize because you can't have multiple groups going at the same time, which means it would be hard to add more nodes and data as you go. And for sparse graphs, it would actually be slower because the e log v would then be bigger. So real-life applications for both of these algorithms are all over the place. These are some really useful algorithms. These include power grids, for example, because you'd want to connect everything, but you want to use the least amount of materials and building costs for it, so you'd want to connect it at the lowest cost. Same logic goes to water distribution and gas distribution, because those things you don't want to spend more money building unnecessary pipes. It also works really well for GPS systems because, like Google Maps, for example, if you want to find the fastest route from A to B, you can have multiple nodes and can find the shortest path between them, the least cost path between them. It's also useful for image segmentation and computer vision and multiple other things. These are the contributions I have. I'm a one-man team here, the only one who did this presentation, so completely me, everything. And then these are my citations. Thank you for listening.